So we're going to learn our first technique now for solving differential equations. This is section 9.3 called separable equations. Our first differential equations technique. Okay. So suppose we have a differential equation of the following type. So what this is saying is, suppose that we have a differential equation which can be written as a function of x divided by a function of y. Then the following I'm going to call this guy star. Then this formula, the integral of h equals the integral of g plus c, implicitly solves the differential equation. Okay. So this is a solution. This is our first technique for how to solve a differential equation. You just have to integrate both functions. So what is the proof of this? Well, all we have to do is take the derivative of both sides of star. If you take the derivative of the left side, you get the derivative of h, the integral of h of y dy is h of y times dy dx. This is just the chain rule and the fundamental theorem of calculus. And if you take the derivative of the right side, you just get g of x. But this implies exactly that dy dx is equal to g of x over h of y. Okay. And this, again, this part is true because of the fundamental theorem of calculus part 1. And that's our proof. Now you might wonder, why is this called a separable equation? The idea is the following mnemonic, okay? So useful algorithm for solving a separable differential equation. So the whole point is that if you see something that looks like this, dy dx is equal to g of x over h of y, what you do is you separate the terms, then integrate. Right? What does this become? You could actually write it this way, using cross multiplication. Now I know what I just wrote doesn't really make any sense, because what do dy and dx mean separately? But then we just integrate both sides and it does make sense. And this leads us to the answer. So this is why it's called separable. It's because you can separate it in this form. All right? So I like to say the steps are separate and then integrate. Okay, so let's go ahead and do some examples. We're going to solve the differential equation. dy dx is equal to x e to the negative y. Okay, so what do we do from here? We're going to multiply both sides by e to the y. And so here's what we get. We get e to the y dy is equal to x dx. Okay, what I've done is just multiplied both sides by e to the y and also multiplied by dx. And notice that we were able to separate the two functions. So if we integrate both sides, what does this become? The left becomes e to the y, and the right becomes 1/2 x squared plus c. And this is our solution. Now we can solve for y if we want to. You don't have to do that, but if you want to solve for y, if you take the natural log of both sides, you get y equals the natural log of 1/2 x squared plus c. Yes, the plus c has to go within the natural log. You cannot separate it from there. Either of these are considered answers. It's not that one is any better than the other. If you can get y by itself, you might want to do that, but you don't have to do that. Okay, let's try another example. Okay, dz dt plus e to the t plus z is equal to 0. Now this does not look separable, right? And this is can be the tricky part of these kinds of problems, is if it doesn't look separable, you still need to be able to recognize that it is. So here's what we're going to do. What I'm going to do first is I'm going to move this guy over to the other side by subtracting e to the t plus z on both sides. This gives me dz dt equals negative e to the t plus z. Now, in order for us to separate this correctly, we need to remember a rule of exponents. E to the t plus z, let me write this rule over here. Let's recall that a to the m times a to the n is equal to a to the m plus n. This is a rule from algebra. So that means that I can actually write the right side of this in a different way. What I did is I separated it into two pieces like this. Now this is nice because it's clear that we can separate the variables. So what I'm going to do is divide both sides by e to the z, and I end up with the following. How do you integrate 1 over e to the z? Because if I integrate both sides, I have to integrate that. Now, be careful, you cannot integrate 1 over e to the z in this form. Instead, let's remember that it's actually the same as this. So now it should be clear how to integrate. The left side becomes negative e to the negative z, and this is going to equal negative e to the t plus c. So we can leave our answer this way, or we could try to isolate z. Z is the dependent variable here. So how would we isolate z? Well, if I multiply both sides by -1, I get e to the negative z is equal to e to the t minus c. Then if I take the natural log of both sides, I get negative z is equal to the natural log of e to the t minus c. And then if I divide both sides by -1, I end up with z equals negative natural log of e to the t minus c. So this is another way that we could leave the answer if we want to have z by itself. Okay. Okay. Let's do another one. How about the following differential equation? dl dt. Actually, let me write the instructions a little bit different here. This time I'm going to write to solve the initial value problem. This is going to be our first initial value problem that we're solving. dl dt is equal to k L squared ln of t, where L of 1 is equal to -1. I just want to say here that k is a constant. So don't let the fact that k is a variable confuse you. K is any number. It could be the number 5, the number 7, it doesn't matter. But it's not a variable. Okay, so how do you solve an IVP? You need to apply both conditions, but first things first, we're going to treat this like a separable equation. Okay, we notice that the variables are clearly separable. How would we separate it? If I divide both sides here by L squared, and also if I move the dt over, I get the following. I get 1 over L squared dl is equal to k ln of t dt. Or, easier to integrate if I write it this way. L to the -2 dl is equal to k ln of t dt. And now I'm just going to integrate both sides. What's the integral of the left side? Well, we need to use the power rule, right? The integral of L to the -2 gives us, remember, you add 1 to the exponent, that's L to the -1, and then you divide by -1. So you get -1 over L is equal to, how do you integrate the right side? Well, using integration by parts, let me remind you of a formula that we did. Using integration by parts, the integral of ln of x is equal to x ln of x minus x. This is the very first example that we did in 7.1, the integration by parts section. So using that fact, just replace x with t and pull the k out because k is a constant, you get the following. This is what we get. So from here, we could get L by itself, but actually our goal now is to use this initial condition, okay? Let's look at this initial condition right here. This is saying that when t is 1, L is -1. So let's go ahead and plug those in so that we can find C. Okay, so what we're doing now is we are finding C. So if we plug those in, we get the following. T is 1. The natural log of 1 is 0, and so here's what we end up with. So if we solve for c, we get c is k plus 1. Once you find c, plug it back into our solution. Sorry, I meant to draw it over to here, right? In other words, we're going to replace that c with k plus 1. So our solution, negative 1 over L is equal to k times t ln t minus t plus k plus 1. You could solve for L here if you wanted to. It's not necessary. So I'm going to go ahead and leave the answer this way. So as a lesson here, let me just write a reminder. When solving an initial value problem, plug in your initial condition in order to find C at the end. Okay, this is really important. You have to do this at the end of your problem or it's not considered a correct answer. Okay. So we are going to learn one more thing here. We're going to learn an important application called mixing problems. So what is the situation? The situation is that we have a tank of fixed capacity containing a fluid which is well mixed with some substance. Okay, so you've got this tank with fluid in there, and then you start pouring in a fluid with a particular concentration of the substance. So a fluid with a certain, how about instead of the certain, how about I'll write with a fixed concentration is added to the tank at a given rate while at the same time the well-mixed fluid leaves at a given rate. Okay, so this is the situation. We're going to learn how to solve a problem of this type, and in fact it is going to turn into a separable equation So let me just say this usually leads to a separable differential equation. So all we need to do is learn how to write this as a separable differential equation and then solve it. So let's do our example. Let me write the example we're going to do. This is problem 4. A tank contains 20 kilograms of salt dissolved in 5,000 liters of water. Brine that contains 0.03 kilograms of salt per liter of water enters the tank at a rate of 25 liters per minute. The well-mixed solution drains from the tank at the same rate. How much salt remains in the tank after half an hour? So this is the problem that we're going to be working on, and it does help immensely to draw a diagram for this. So let's do that on the next slide. Here is our tank. And let's go ahead and write down what we know. Well, okay, hold on. Let me back up a minute. It says how much salt remains in the tank after a half an hour. So it makes sense that we are going to create a variable. And so let's write to let y of t equal the amount of salt after t, I'm going to use minutes, okay, because the problem is written in terms of minutes at one point. So let y of t be the amount of salt in the tank after t minutes. So let's think about what's happening. At the very beginning, we've got 20 kilograms of salt in the tank, right? And so that means we start off with y of 0 is equal to 20. It's worth noting that y of t is going to be in kilograms, so I'm going to put that there. This is why I can say that y of 0 is equal to 20. Now that does not, this is not the differential equation itself, but this is going to be part of it. It's going to be an initial value problem. So let's think about what is coming in first. It says brine that contains 0.03 kilograms of salt per liter enters the tank at a rate of 25 liters per minute. Okay, so let's go ahead and draw a little arrow here. What's coming in is something that's 0.03 kilograms of salt per liter, and it's also coming in at 25 liters per minute. Okay. Then it says that it leaves the tank at the same rate and it's kept thoroughly mixed. So it comes out and it leaves also at 25 liters per minute. Now, right here, this is the concentration coming in. But we are not given the concentration coming out, and that is the tricky part here. So the thing to notice is that the amount of concentration coming out is changing at all times, and this is why we are actually going to need a differential equation. So how much actual volume of liquid is in the tank? So let's let V of t equal the amount of liquid in the tank after t minutes. Now, it turns out that because these two rates are the same, right? We have a 25 liter per minute coming in and 25 liters per minute coming out. This actually means that the volume never changes, so it's just a constant. So because we started out at 5,000 liters, this means that we always have 5,000 liters. So V of t is just a constant function of 5,000. This is not always going to be true. So just be careful. If the rates are different, you are going to have a function of t here. Okay, so then, what would the concentration be in the tank at any moment that's coming out? Well, the amount of salt in the tank is Y, and the amount of liquid in the tank is 5,000, so the concentration is going to be Y of t divided by 5,000. So this is the concentration coming in. And yes, it depends on Y. And this is exactly why we have a differential equation. So how do we write the differential equation? Well, it looks like this. dy dt, remember, this is the rate of change of the salt per minute. This is equal to the rate, let me call it this, the rate of the salt coming in minus the rate of salt coming out. What's the rate of the salt coming in? It's going to be 0.03 kilograms of salt per liter times 25 liters per minute minus y of t over 5,000. Remember, this is in kilograms of salt, and this is in liters, times 25 liters per minute. Why did I write units? I wanted to write units to show you that the units cancel accordingly, and you do end up with kilograms of salt per minute, which is what a dy dt should be. Okay? So let's go ahead and write the differential equation then on the next page in a simplified form. We have dy dt is equal to 0.03 times 25 is what? Let's see, 3 times 25 is 75, but this is going to be 0.75, right? So it's going to be 0.75 minus, and if we look here, we get y of t times 25 over 5,000. Okay, y of t times 25 over 5,000. So if you reduce that, that is actually 200, so it's going to look like this. If that's a 1, and this is a 200, we actually end up with the following. It just becomes y over 200. Or let's go ahead and write it this way. Isn't this the same as dy dt is equal to 75 over 100 minus y over 200? Okay, so if you want to get a common denominator, you can. You actually just multiply both by 2, and so this leads us to the following initial value problem. I'm going to write it this way. dy dt is equal to 150 minus y over 200. How did I get that? Again, I multiplied this by 2 and this by 2 in order to get a common denominator. Now, this isn't it. We also know that y of 0 is equal to, what was it? It was 20. And this is all part of the initial value problem. This is what we are solving, guys. So how do we solve such a differential equation? Guess what? It's separable. So we're going to write it this way. We have dy is equal to this. And if we integrate both sides, we end up with, the left side is negative natural log of 150 minus y. And the right side is equal to t over 200 plus c. Now, of course, we do need to figure out what c is. Okay, so let's use the fact that y of 0 is equal to 200. Or sorry, y of 0 is equal to 20. This means that when t is 0, y is 20. So we plug those things in. Negative natural log of absolute value of 150 minus 20 is equal to, t is 0, so that's gone, is just equal to c. Which means that c is equal to negative natural log of 130. Because the absolute value of 150 minus 20 is the absolute value of 130, which is just 130. So you end up with the following. Negative ln of, so here's what I'm doing just before I write this down. I'm taking this guy and I'm substituting it for c right here in my differential equation solution. I get negative ln of 150 minus y is equal to t over 200 minus the natural log of 130. So what do I do from here? From here, I just have to get y by itself, and then I can figure out how much salt is in the tank after 30 minutes, right? Half an hour. So I'm going to multiply both sides by negative 1. I get ln of absolute value 150 minus y is equal to negative t over 200 plus the natural log of 130. From here, I raise e to the power of both sides, and I end up with, let me go to the next line here. The absolute value of 150 minus y is equal to, and if I raise the right side to e, I get e to the negative t over 200 plus ln of 130. But this right side actually becomes e to the negative t over 200 e to the ln of 130, which is the same as 130 e to the negative t over 200. So I get this. Now we have an absolute value equation, which means you actually get two potential solutions, right? Let me go ahead and write them both down, and then I'll show you guys which one to pick. So this means that 150 minus y is equal to plus or minus 130 e to the negative t over 200. Or if I solve for y, I actually get y is equal to 150 plus or minus 130 e to the negative t over 200. Okay. Now, which one do I use? Well, I want you to recall that when t is equal to 0, y is equal to 20, right? This was our initial condition. That is only true if we use the minus, right? Because if you plug in 0 for t, you actually get either 150 plus 130 or 150 minus 130. We have to use the minus sign. So this means that y of t is equal to 150 minus 130 e to the negative t over 200. So we just found the amount of salt in the tank after any time. And so finally, let's recall what the problem originally asked. It said, how much salt is in the tank after a half hour? A half hour is 30 minutes. So we just plug 30 in. We end up with 150 minus 130 e to the negative 30 over 200, which is equal to 150 minus 130 e to the negative 3 over 20. Now, this is an amount of salt in kilograms. We can leave the answer like this if we want an exact answer. However, if we want an approximate answer, we just put this in our calculator. I'm going to write 150 minus 130 times e to the power of negative 3 over 20. I actually end up with approximately 38.11 kilograms of salt. So this would be considered the approximate answer, but what I wrote above is the exact answer. This algorithm, guys, of doing this problem always works, okay? So this is the main thing you want to focus on, which is how to do the setup. Thanks very much for watching, guys. I'll see you in the next video.